Good afternoon. As you certainly realize, my native language is Polish, but I have the slides prepared in English, and I'll speak my Polish English. So first of all, before I start, let me say an anecdote. I've been friends with Dr. Pablo Orduña for some years now, and we have met at various EduCon conferences which he mentioned. And there was in Istanbul, I think 3 or 4 years ago, or maybe even 5 years ago, when after the conference and after some activities, like social activities, we are sitting in a Turkish restaurant, drinking beer. There's 4 or 5 of us, and I was taking pictures, and at one point I took pictures of some Turkish ladies, and a few moments later a couple of Turkish gentlemen approached me asking to delete these pictures, and I didn't realize that there are differences in cultures, right? And I got Americanized, so American culture is very open, and the Turkish culture not so much. And then I tried to oppose this request, and I didn't comply. And then Pablo, who is bigger than me, and like wider arms, entered the conversation and convinced these 2 folks to calm down, that everything will get all right, and I decided to delete these pictures. So, so since then, I believe we are friends. At least I consider Pablo my friend. So when we met yesterday at the hotel in the evening, Pablo asked me, Janusz, and there was a refrigerator. Pablo asked me, Janusz, which beer shall I drink, Okocim or Tychy? And I said, I'll give you the advice for a small favor. Pablo said, yes. So choose Okocim. And then he asked me, what's the favor which I owe you? So I said, could you please shorten your presentation by 15 minutes in favor of mine? And he said, well, then I must speak faster. I will speak faster. So this is what happened today. And contrary to what the chairman, Mr. Chairman said, I will use the 60 minutes for my presentation. So this is the first slide, and I have this photo of mine in front of the Google headquarters, because it's very relevant. Everybody uses internet. Everybody praises Google, and so on and so on. But it's only 99.9999%, I'm assuming, although I didn't do any statistical comparisons, it's just downloading pages, right? What pages? These are all documents, as Dr. Tlauka mentioned. These physicists at CERN, Tim Berners-Lee and others, they just created the first web page years ago, and that was just a document, right? There's only a difference in the medium. All the web pages are documents. So every day we are downloading, all of us, thousands and thousands of web pages. And that's what Google does, provides us with those web pages and links to all of those distributed around the world. But the essence of this technology which we are talking about today, which Pablo did, and I will give you a little bit broader view, is within this framework, but it's essentially very different, because this is more educational, and we are the creators. We, the clients, the users, we are the creators. So this picture here, the title page, is sort of used here to contradict what actually is expecting us, and our children certainly. The title of this talk is creating network smart learning objects for online laboratories according to the IEEE standard 1876. And I'll start this presentation a little bit differently, because rather than providing a talked outline in the first slide, in the second slide, I'm providing, I would call it a sneak preview from actually it's from the garage, from the hangar actually for helicopters, and one of the NASA centers I'll talk about in a second. So what is a preamble, which I call? Well, in bullets, it actually dissects the title, because as the title is formulated, I will talk about the creation process a little bit for remote laboratories, for online laboratories, using learning objects, right? And involving standardization. So all these components of the title are here in the sneak preview, which I call a preamble. And now the actual talk outline is follows this title and the preamble, because first, and gathering from your questions and comments during the interaction with Pablo, an essential thing in using online labs is not necessarily the technical part, but a lot of it, maybe even more important than the technical part, is the motivation. Why should we use these labs, and what are the consequences? So I'll talk a little bit about the motivation, why online labs are needed. Then I'll explain what we think, people who develop these standards, and Pablo is one of them, how they understand the learning object. And then I'll show just maybe a couple of slides regarding the standardization, because the standard is, reading the standard and even talking about it is extremely boring, because like for the standard of, let's say, Ethernet, right? There is a lot of very exact engineering specifications, and you don't want to hear that during a talk. You may talk about this during a technical discussion with someone who's developing an Ethernet chip or board or something like that. Same here. The standard is available, and it simply is full of technical specifications. So I will only touch it, right? And what Pablo didn't talk about that much, because he showed you the user part, the client part, I'll try to say a few words how to make an online lab, how to make your lab an online. And I will conclude with some observations, which I think are very important from the point of view of the consequences and impact of these technologies. So what is the most important piece? What are the most important pieces of the motivation? I think that it was actually mentioned a couple of times in Dr. Klauka's presentation, and also implicitly included in Pablo's talk, that computer systems nowadays are used around the world in very demanding applications, and the number of these applications is increasing constantly every day, regarding the remote access to online access to remote services. It's not that we force the use of online labs, but the actual reality, the industry is forcing them. What I have here are the most demanding applications, right? Such as flight control systems, accelerator control, and I'll show examples, space missions, road vehicle control, and so on. All this, even though the computers control devices, mostly moving devices, but they can be accessed remotely. This is the reality, and it'll become more and more and more and more a reality, and that cannot be avoided. So we have to educate engineers in these technologies, whether we want it or not. And it's not because there's just this trend in education towards online teaching, online labs. No, this is because the industry requires it and will require it even more. So now I'll show you some examples, and maybe with comments and with some additional insight. So regarding vehicle control, this is a picture from one of my summers spent at the Air Force lab, where I hijacked the locomotive. I hijacked the Air Force locomotive because I knew how to do it. I studied that before, and that is just a sort of a joke, but everybody understands what it means, remote access to a vehicle. Then this is not a joke. This is from the Fermilab, and everybody heard the term LHC, Large Hadron Collider, or in Polish, Wielki Zderzacz Hadronów, which is operating at CERN in Geneva. So when I went to Fermilab, I was introduced to the control room, where the physicists, the same folks who, or dear colleagues of these folks who invented the World Wide Web, their reason to invent the World Wide Web was to give access, remote access to physics experiments at CERN, actually. So this is the control room in Fermilab, from which we're able to access the accelerators at CERN, right? And there are other examples, like flight control systems, which the United States Air Force is developing. Simply drones, we can call them drones, right? And there is another example of a device, of a robotic device, which is being sent, which has been sent several times to Mars, a Pathfinder mission. An interesting anecdote about this is that the first Pathfinder mission failed because the robotic device got stuck on Mars and nobody knew what happened. So the control center people in Pasadena analyzed in California, analyzed the behavior of the software and of the robot, and found the bug offline, found the bug in software on Earth, fixed the bug, and re-uploaded the operating system to the robot, to Mars. That was like maybe 15 years ago, the first Pathfinder mission. So this convinced me ultimately that teaching students how to do the remote laboratories, not only how to use them, like in physics, chemistry, biology, and other sciences, they mostly use remote laboratories. In computer engineering, and Pablo is a computer engineer like me, we develop them, and we teach our students how to develop software for remote devices, to upload the software there and control these devices. So you've seen this using the VHDL for the FPGA boards, and you've seen it for the Arduino boards using the a simple programming language for Arduino. So that's still motivation number one, right? There's another example here with the wind tunnel in the Ames Center in California, the NASA Center, which is familiar to Pablo as well. This is a local device. The wind tunnel is a huge device with an extremely complicated control system. So of course the control room for this wind tunnel, for the device, is remote as well, but is remote in a sense that's in a different room. So now this is an example that is showing all of us that the remote doesn't mean on distance. Remote can mean in a different room. So if you understand that certain devices, for safety reasons, for example, can be controlled from another room, then what's the difference to have this control room located 1,000 or 2,000 kilometers away from the real device? So this is exactly the same thing. But this leads us to a very important motivation item, which is everybody is talking, at least in the West, I think in Poland as well, about teaching STEM, more students, engage more students in the science, technology and engineering, because that's the future of all nations who want to be technologically advanced. So this is, of course, all related, but this is my motivation point number 2. And there is motivation number 3, which is that in engineering curricula, laboratories, hands-on laboratories, right? Not remote laboratories, but laboratories which we call hands-on, that students actually touch the device with their fingers, right? May have various difficulties in operation. And certainly the devices use sophisticated hardware and software. And for this, the third bullet says that if we have a hands-on lab, we need to have an adequate technical support, right? Well, who of the smartest people, and I'm not offending those who stay here because I know some of them, who stays for the salaries in the academic environment as a technician and worker in school maintaining these labs, right? 90%, if not more, of these people leave after the first year because they educate themselves, they learn how to do these things, and they double their salaries outside. So they don't stay at the university. Therefore, this is the third motivation item. Why do we need online laboratories, and why they will actually, I would say, prevail. So that's the first part of my talk regarding the motivation. Then there is a notion of a learning object. I'm sure that everybody present in this room knows what a learning object is for their own sake. But for the standard, you must provide the definition to make sure that we are on the same page, that everybody talks about the same concept, the same notion. So there is a definition of a learning object for standardization purposes in another IEEE standard. So it says that a learning object is an entity, digital or not, that can be used for learning, education, or training. And I'm very well, I'm fluent in correcting definitions. So I said the same thing in a more compact manner and making more sense. That a learning object for this standard is something like an entity, most commonly a device, but not only, encapsulating certain educational functions. And you'll see in a second that this definition much better describes what a learning object is. And the essence is that this entity encapsulates educational functions. So a few more words on learning objects. Examples which we could use, maybe a cell phone, right? Which we can use for educational purposes, provided that we understand what particular functions are in place for the purpose of education. Then robots, as Pablo showed, websites, just websites, can be a perfect example of an educational object if we understand what are the specific educational functions which the website provides, and not just any website. And here's the key, the second bullet tells it all. These functions are accessible, must be accessible through well-defined interfaces. Because through these interfaces, we call the functions to perform predetermined learning activities. This is the essence. So interfaces are the key to define the learning object, not what is inside a learning object, but how it is preferred to be used. So the students interact with learning objects through the interfaces. And there are more examples here. That these are the electronic boards which Pablo showed, FPGA boards, robotic devices. There's more, because we can expand this, adding learning objects which we think could fit into this definition. So sensor networks, even solar plants, and there's probably hundreds more. But also web pages, modules, which we offer to students online for educational purposes. But here's the surprise. Textbooks match the definition of a learning object, because there's only a few activities which the students can do as requested by the instructor, right? In the old teaching style, we ask the students to, after the lecture, to read a certain part of the textbook, and there were exercises at the end of the textbook chapter, and so on and so on. So the definition is actually encompassing everything which can serve the educational purposes, not only electronic media, but also traditional media. Besides, textbooks are now electronic as well. So there were a lot of reasons why this working group was formed. The IEEE, and I may not be educating everyone here, but I want to mention this. IEEE is the American Organization of Electrical and Electronics Engineers, and it has its branch named Standard Association. So IEEE is organized in societies. There's a computer society, industrial automation society, 24 others, and among them there's an education society. So Pablo and I are members of the IEEE Education Society, and they formed a working group for the Network Smart Learning Objects for Online Laboratories standard, and we obtained this number from the Standard Association, 1876, and we started meeting and developing, and what happened after maybe 5 or 6 years, it's a very laborious process, because it's all very bureaucratic. A standard, as you can imagine, is the notion of a standard is very critical in computing. We wouldn't be able to use internet without Ethernet, right? You plug your computer into the Ethernet port, or you just don't do this, you use your wireless network, but it's all standardized. The only reason we can so easily, the major reason we can so easily access internet, World Wide Web, and so on, is because that has been standardized by folks from IEEE. Then these standards, when approved by IEEE, very often become international standards, because ISO, and International Electrotechnical Commission, IEC, they approve these standards by asking dear members around the world whether they agree with this or have comments and so on. So that's a brief information for someone who doesn't know how this all works. So that's about learning objects, what they are, but that's not the end of it yet. And what is the example here? Oh, sorry, I'm getting backwards. So now, here's maybe an overview of what Pablo showed in practice, and pretty much what you have to put on the table and understand when you want to develop your own lab and offer it to students or to, let's say, a sister organization or a bigger platform to incorporate this this online lab into a broader picture, right? So on the left, on the I guess right-hand side, you have all these devices, right? And the interfaces actually to these devices should be standardized if you want to be part of the broader platform, larger platform. And you normally have, this can be one computer, but the lab server has access to, it's a computer, and I'll talk about the software in a second. So the lab server handles the laboratory part, and there may be also another computer, a web server, which provides access from the external world. That's the logic, right? So now, here we come to the IEEE standard 1876, how this is organized. So these little diagrams here are crucial to understand what is in the standard. We have devices and users, and the users can interact with the devices, either send signals to devices or retrieve certain signals from them. And that's the traditional notion of the lab, which you have, there are such in the buildings in this university. There is a lab station, right? And the students have the lab manual, and they actually operate like logically shown in this primitive diagram. They send some signals or request certain actions from these devices and obtain the responses, and they provide a record of their experiments, their measurements, and then analyze them for the purpose of passing the lab and learning, right? So, but this is not the part of the standard. Therefore, the little rectangle is drawn with a dotted line. What is a part of the standard is the layer above it, which is called lab as a service. So what the students were doing manually in here, right? Now, a lab as a service layer is providing. So this is a part of what Pablo showed, but he didn't talk about it because he's a salesman. He wanted to attract the audience. But I provide some sort of analysis, right? How this all works layer by layer, because the standard actually does it. So this is called lab as a service, and the students do not deal with signals to the lab devices. The students deal with higher level abstraction, right? As we will see what kinds of abstractions are those, but mostly these are also lower level functions, not dealing with signals, but dealing with services. And I'll talk about that in a second, after I have finished the entire hierarchy of these layers in the standards view of the online laboratory. So above the layer of lab as a service, LAAS, here are the learning objects. So the learning objects play a role of responding to certain students' activities. So the students, let's say, have a task of analyzing a certain physical phenomena. So if they have the task of analyzing the physical phenomena, the instruction manual for this lab tells them what data to collect, right? So these are the activities. They engage a learning object into the action, right? And the learning object knows, the student doesn't. The learning object knows what services to call, and the lab as a service layer, it's all software. I'll show you in a second how does that map onto the architecture of the lab. So the lab as a service knows how to respond to the learning object's request for service, and issues a certain signal or more, and handles the response of the hardware and provides the result to the learning object, and the student knows what happened. The next layer is what Pablo mentioned very briefly, that we can place all this into the learning management system, right? Which may be a MOOC platform or other LMS and so on. So that's the whole hierarchy. But the standard covers only layer 1 and a little bit of layer 2 with recommendations. Layer 1 is covered with mandatory requirements. Of course, in addition to this, you need to have security provided, right? And in a form of authentication, authorization, and things like this. So each layer above the hardware layer has this, plus the teacher, the instructor, has to have full knowledge of what happened, right? So recording is also needed for each of these layers of the actions taking place at the particular layer. And this is where I wanted to finish explaining the essence of the standard, because when we go more deeply, you will see the code. And to the audience like this, I don't want to show too much code or certain requirements expressed in the metadata language and so on. So I'll only mention that briefly in 2 slides, that there are some required services, right, at the level of the lab as a service. And they are pretty natural, because what are these signals above the hardware and software layer? These signals are only of 2 sorts. There's nothing else. I don't know if you realize, there's nothing else in computing, only reading data and writing data. There's nothing else. So, consequently, we have sensor data and actuator data, right? At the low level, of course. That's what I mean. If you have the memory location, you can only read it or write it. So here, get sensor data, metadata, get actuator metadata, set actuator data, and get and set configuration. This is the 3rd class of services. This is our business. I mean, developers of these online labs. The student who is at the higher level above the learning object never looks at this, never realizes that there are some function calls which are required by the standard to do the job which the student is given by an instructor. There are some optional services such as these. Get experiment, for example, is important, but I will not talk about it because I would have to get into more details. So the standard also has an appendix how folks who worked on the standards actually implemented it in their labs. And this is, I will not talk much about it because you can look at it in the standard, but even better, you can find, if you're interested, you can find respective articles on the web, because these folks have published a lot about their lab. So Mach-Zehnder interferometer, GRASP is a very popular platform. That's how they show here how they, in this appendix from the standard, therefore I have this notice here that's courtesy the Standards Association. How they implemented layer 1 and layer 0, then the other layers 2 and 3, and there is another example in the appendix to the standard. There's the pendulum lab. So these folks show how they implemented their standard layers in their laboratory. And sorry for flashing this without further explanation. I just wanted to show that it is there in the standard, and anybody interested can look at it. What I wanted to do in this talk is focus on concepts mostly. So now, one of these labs also includes the entire architecture, right? So you see here that it's not much different from the generic architecture which I showed maybe 10 or 12 slides before, that you have the internet, you have various clients, right? Laptops, smartphones, etc. It goes to the public IP marked here, which is a server like LMS or Moodle server, right? And it must go also through the authentication server. This is where Pablo logged on to his labs land, right? And then it has internal network in which local lab servers operate, which handle particular devices on the right-hand side. So these local lab servers, there may be not necessarily local, they may be remote. Second column from the right. These servers may be located in these labs and universities and institutions which Pablo showed you they are connected to the labs land, right? And each of these local or remote lab servers handles their own devices. So, so now this is everything about the standard. So I'm closing talking about the standard. And now, how did I implement it in my school, which is Florida Gulf Coast University? So essentially the same picture is here. We have a number of lab devices. This diagram may not be current because I will show you in a few more slides, and there is very many of them because we have probably automatized maybe 50 or 60 different devices. It's been going on for years. Not according to the standard, of course, not according to the IEEE standard, but once you know how to do it, you can easily adjust it to follow the rules of the guidelines of the IEEE standard for networking smart learning objects. By the way, I never mentioned what is the meaning of the word smart, right? I only explained what is a learning object. Well, smart is not very smart, but smart, the word smart in the title of the standard means that it's something more than just a web page to download. So you may know or not that there are essentially 3 different kinds of web pages. There are static web pages, pretty much HTML web pages which you can only download, right? There are dynamic web pages. Nowadays, the most important part of the internet, where you make a request to the server for certain data. The server initializes the program, the software, to collect the data, for example, to access the database and so on, puts together a web page corresponding to the request, and this web page is then sent back to the client who requested the service. So this is what we call smart in this standard, as opposed to static web pages downloading information only. So now you see a big difference here, answering, I think, one of the questions. Oh, Pablo's question. Why there is so many online courses for, let's say, for non-engineering disciplines? Because developing these pages is very trivial, developing these static pages. And who, for goodness sake, in philosophy would require a dynamic web page, right? All what they talk about in philosophy is can be just encompassed in static web pages. They download a lot of information, then discuss it in great simplicity, of course, as opposed to engineering disciplines, right? We need to collect data as a result of experiments. So this is why there is a big difference, and there is a very few compared to, let's say, humanities, very few online courses for engineering disciplines. That's the main reason. They use only static web pages. We use dynamic web pages. There is a third category of web pages, active web pages, for which actually the execution of the code occurs on the client side. JavaScript was created for that, but that's putting this aside. So we have what we have here is the lab at FGCU, which has the same architecture as shown in the previous slides, but it doesn't follow the IEEE standard because it was created long before the standard got into the picture. So now, and here's another important point. Before I will show selected devices in this lab. And this is what Pablo sort of missed explaining, and I'm not blaming him because he did it deliberately to let me explain it, that the labs can be categorized into batch online laboratories, which means the students provide a request, right? And the request tells everything to the server. The server analyzes the request, collects the data, and returns the result. This is sort of observational category for operating online laboratories. There is a sensor type of online laboratories which rely on collecting data in real time. So some of these examples which Pablo showed are of that sort, and there is an interactive online labs in which the students set parameters, right? This is also shown by Pablo, and then depending on the parameters, the server behaves accordingly, right? But now, and this was visible maybe, and not everybody realized that there is this strict categorization. But now, all these labs are passive. What Pablo also showed is invasive labs. That's my term. Invasive labs allow the student to write the code and upload the code to the server and then see what is the behavior of the device to which the code was uploaded, whether it performs the functions as requested. But this case is only important for computer engineering and software engineering, because the physicists, mechanical engineers, chemists, right, environmental engineers, they don't care what the code, what is the code which runs their labs, right? They only care about collecting data in one of these three manners: batch, sensor, or interactive. But we are computer engineers, so we have to have a broader view of online laboratories. We teach students how to program these remote devices. And when I mentioned the, remember at the beginning when I mentioned the Pathfinder mission to Mars, that was exactly what sort of sparked my imagination. That, well, yes, I'm a computer engineer and teaching students how to develop software, so I have to tell them what to do to repeat this extraordinary accomplishment that their code went to Mars and the robot just miraculously moved because the bug was fixed. So this is called invasive labs. And now I have a lot of devices in these slides which I don't want to bore you with, I will just very quickly skip over those because I want to get to the conclusion. And I don't want to upset the session chairman that I'm taking the time which I don't deserve. So here are some of these devices. Repeat what Pablo showed. Some of them are different. So for example, there is a microcontroller which happens to be an Atmel microcontroller that performs certain measurement functions, right? And there was a remote access to it. Every purpose of having this remote access device is shown here. Then there was, this is about the operating system you never heard of. Anyone in this room knows about the VxWorks operating system? No, because this is an operating system. Why Windows or even Linux will not control anything which is safety critical, for example, which goes to space, because they are not reliable enough. VxWorks, it's just called a real-time kernel, another operating system, was developed by folks in one of the nuclear labs in Berkeley, California. So, and that's a part of our software engineering program. So VxWorks controlled this Pathfinder mission. And now if you see anything extraordinary accomplished by NASA in space, you can be sure that VxWorks controlled this mission because it's so reliable. And if they found a bug, they admitted it, but they fixed it and uploaded it to Pathfinder on Mars. So anyway, so this is one of the projects, and of course VxWorks is available in our lab, and we have provided remote access to it. Then FPGA lab, of course, we had this, but it's now not functioning. Guess why? Because our management and my school decided to get rid of digital systems course in the software engineering program. They said it's unimportant for software engineers. So anyway, but the devices are still there, Altera and Xilinx. Of course, wireless sensor networks, that is another lab. We had a project from an external customer who wanted to have a wireless network accessible remotely. But then guess what? They realized that students can never, within 1 or 2 semesters, can never deliver industrial quality software, which is true, and I admitted it. But they needed industrial quality software, so they, after this experience with us, which was very positive for them because they learned what are the weak points, they simply ordered the software from a professional vendor. This is interesting. Smartwatch and Android. So smartwatch sends the health data to the Android, and Android communicates with the Internet of Things cloud. So there was a project, not that much accessing the lab device over the internet, but providing the internet service for the clients like doctors and patients to just to have current data about the patient. Another example is to control a device at home with a microcontroller board. Another example is the data acquisition and control done remotely. So this is, like Pablo has plenty of examples of that. Then we got into the robotics, and we have like a dozen of different robotic devices. And of course, 3D printer is one of them. 3D printers are very rarely equipped with internet connectivity. This is because it's dangerous, right? A 3D printer device does some mechanical things which, if it goes astray, right, the person may be responsible. A person who manages the lab may be responsible for this. Yes? Yeah, I'm assuming my time is 5:15. Yes, that's in the program. That's in the program. I traded 15 minutes with Pablo. No, I can finish in 5 minutes. All right. I can finish in 5 minutes for the benefit of the conference participants. I know I'm getting boring, right? So, and we have, so about robotic devices, we all know, right? So 3D printer is one of them. Then there is robotic arms, like this. Then there are humanoid robots, robots on wheels, and also, importantly, Lego robots are not equipped, at least to my knowledge, with internet connectivity, at least with good internet connectivity. And nowadays, people use Arduino, as Pablo showed, Raspberry Pi. So these devices can be also accessed over the internet in a lab for the purpose of students to learn. And drones. And please don't start clapping. I'm not finished yet, but I have the conclusion. This is very important. What is the conclusion? There are several points here which I want to make. First of all, there's a tendency of education, there has been for some time, to replace boring lectures by something which would attract students. And we all compete in the educational environment, in the college environment, to attract best students, right? So we started using graphics, animation, interaction, simulations, and now online labs is the thing. So my view of online labs, Pablo is very modest and he never mentioned this, but to me, online labs are the disruptive technology, which means that they will very quickly, if there is something who wants to invest, and I wish Pablo the best to find investors in Silicon Valley, they will very quickly, online labs, become a dominant technology in education, in engineering education, I mean. How does that happen? Well, here is a little comparison. People invented clocks not so long ago. And as this gentleman named Louis Mumford stated, that upon invention of a clock, right, one quit to eat when they were hungry. They started to eat because the watch, wanted them to eat. They slept, not because they were tired, but because the clock wanted them to do so. Then another gentleman named Marshall McLuhan, in his book, The Medium is the Message, expressed this brilliant thought that the electronic technology extend our nervous system, right? So now, just like glasses extended our vision, vehicles extended our legs, printing technology in the Gutenberg era extended our speech, electronic media extend our consciousness. And this is all disruptive. And now a couple of Polish accents here. So it's all in English, so Pablo will understand it too. Now, what is disruptive? Look at this Ryszard Kapuściński's book, Heban. I don't know if anyone read this or remembers, because it was published 20 years ago. He gives a brilliant example how a smart shift in technology can change lives of thousands of people, bringing plastic containers to African women, allow them to carry more water, right, on their heads or in their arms, employ their children, because they used ceramic containers before. So that is what the disruptive technology means. Now, how important is that for education? No one can tell. But I can quote another Polish mathematician, Mark Katz, who's a Jewish Polish mathematician educated in Lvov, who emigrated to the United States. How successful that could be in education, I don't know. But if you asked him, he published this in his book, Enigmas of Chance. Was I well educated? Well, I don't know, he said. If education is defined as what is left after one has forgotten most of what one has learned in school, then I guess the answer is yes. So our answer, whether this technology will have any impact, is still in the air. But prediction is it'll have a great impact. So this is the acknowledgement slide that I want to thank the Education Society colleagues for funding this project, in part my school for letting me attend these meetings, at least in part, National Science Foundation for awarding in the distant past the lab, creation of the lab, and Docent Anita Tlauka with her colleagues Magdalena and Isa and her boss for inviting us here.